Hi guys, this is Mrs. Allison. Today we are going to talk about approximating definite integrals, or something we call the Riemann sums. So let's just go ahead and get started and jump into this. So let's consider the curve f of x equals x squared plus 1, and then its shaded area, to compute the area bounded by the curve. Well, we know from everything that we've done so far, what we're going to do is we would take the integral from 0 to 4 of the function, so of x squared plus 1 dx. And we know to do that, we would get x cubed over 3 plus x evaluated from 0 to 4. And then using the fundamental theorem of calculus, we would get 4 cubed would be 64 over 3 plus 12 over 3, right? So 4 plus 12 over 3 would give us 76 over 3, so approximately 25.3333 repeating. Okay, and that's what the area of that curve is. According to the definite integral, we could have used the fundamental theorem of calculus, we could have used our calculator, but I want to use that as a basis to talk about our approximation techniques. And one of the approximation techniques that we have is using rectangles, and that is called the Riemann sums. It's named after a German mathematician, Bernhard Riemann. And he came up with this idea of finding the area under the curve based on rectangles. He did give two stipulations, and the stipulations were that they have bases of equal length, or width, like however you want to look at it, and they have a consistent height drawing rule, meaning that each time we look at a rectangle, it calculates the height the same throughout the whole curve. Now, there are three types of Riemann sums that we're going to look at. We have the first type. I'm going to scroll this up just a little bit. We have the first type, which is the left endpoint, where the left of the rectangle is touching the curve. We have the right endpoint, which is where the right corner of the rectangle is touching the curve. And then we have the midpoint, which would be where the middle of the region touches the curve. Okay. Now, these are best for approximating. Let me just write that down, actually. These are best for approximating values of definite integrals where or when we're given incomplete data. We are not going to look at it such as tables and graphs. Sometimes we don't have enough information to really know what our equation is, and so we can't go through and calculate it by means of integration techniques that we've learned so far. Sorry about that. And so Riemann sums would be the way that we'd want to go. Now, we actually know this area under the curve because we looked at how to calculate it, but I want to look at it in terms of the Riemann sums, just so you can see how it relates back to something we already know. So just keep in mind that this area we got 25.33. Hang tight to that. So what I want to do is I want to sketch the area of each of the rectangles and then find a sum that goes with them for the area under the curve. Now, there's a couple things that we need to note. One, they will usually tell us in a problem something like which type of Riemann sum we're going to take. Now, what this means, this LRAM, it means the left rectangular approximation method. So the right rectangular approximation method, midpoint rectangular approximation method, And then when you see this little subscript right here, this subscript tells us how many rectangles we want in our region. Okay, so when we see L4, it means that we want 4 rectangles. Now, the way that we are going to determine how big each of the rectangles are, because remember they have to have that same width, the base across there. The way that we determine that is we are going to use this formula that says delta x, and I don't really have a whole lot of room in here, so I'm just going to write it up here. Delta x equals b minus a over n, where n is the number of rectangles. So n is that number that we have there. So for this particular diagram, my delta x is going to be b minus a, so 4 minus 0, over 4, because it said we wanted to use 4 rectangles. So I know I want each of my rectangles to have a width of 1. And we can see that across the bottom here. If I look at all of my rectangles, I could divide this region into 4 rectangles, which is what I want as long as the base is 1. Okay, so let's do a left-hand rectangle. Here's what that looks like. What we're going to do is we are going to connect our left corner of our rectangle to the left point in the region, and then we're going to trace it straight across and down. There's my first rectangle. Okay, so I'm going to be finding the area under that. Now we can see that that area is going to be a little bit below the actual value of the curve at that point, or the actual area of the curve at that point, because there's part of that region right here that we can see where it's missing right in there. That's okay. This is why it's called an approximation. Now to get the next left region, well, let's start there actually. I know the area of that rectangle. Well, this is 1 high here. So this is the ordered pair 0, 1. And it's 1 across right here. So this is a 1 by 1 rectangle. And then if I look at my next rectangle, I see that I'm going to start it here and go over. And what you may see here is that this looks even more like an under approximation. And that rectangle is, let's see, that's the point 1, 2. So that rectangle is 2 by 1. And then the next rectangle you'll see is right here. So we're going to go on the left-hand corner of the rectangle, needs to touch the curve. And so the area of this rectangle, let's see, that is the point 5. Oops, 5 times 1 for the width of 1. And then the next left rectangle is right here. And you can really see that this is going to be quite a bit lower than what we got up above, or it should be quite a bit lower. So we have 10 times 1, because this is the ordered pair 3, 10. And if I add all those together, one thing I want you to see is oftentimes these areas will be written where the width of the rectangle, that dx, is factored out. And then we have our left-hand values written like this. So this area is 18. And if you recall, that area that we got using the definite integral was like 25. So it is quite a bit less. Should make sense, though, if we look at this particular problem, that this area seems to be quite a bit less than. Okay, let's move on and let's look at the right rectangular approximation method. In this method, the right corner of my rectangle is going to touch the curve. And so my first rectangle might be drawn like this. And we would be finding the area under this particular rectangle. Well, the height here is 2, and the base is still 1. And I'm going to keep going. So this next right rectangle is right here, and what you can see is that these areas are a little bit bigger than the actual curve. So this was 5 times the width of 1. And then here's my next one. I'm going to stop shading it in. This would be 10 times the width of 1. And then this last one, I have this rectangle here, which is 17 times a width of 1. And again, you may see this written where the width of the rectangle is out front, and then the remaining heights are added together, and we get the area is 34. Well, that's quite a bit higher than the actual area, but that should make sense because when we look at this, we can see that there's quite a bit of area in each of these rectangles that's above the curve. Okay, let's look at how the midpoint might be different. So the midpoint rectangular approximation method. In this method, it's just what it sounds like. We are going to take the midpoint of each region. So if each region is 1, I'm going to go up to where it's 0.5. And I'm going to connect it. And I'm going to go up to where it's 1.5, and I'm going to connect it. And I'm going to go up to where it's 2.5, and I'm not writing the areas at the moment because I'm actually going to calculate them. And then 3.5. So sometimes the midpoint can be tricky to see if we don't actually know the value of the midpoint. It may have to be an estimation. But in each of these, I happen to have the formula. I know this is an x squared plus 1 graph. And if I do 0.5 squared plus 1, I know that that height would be 1.25. So let me write how I got that. So we know this is an x squared plus 1. So I could do 0.5 squared plus 1, so it'd be 1.25. And then I would just repeat that process for each of the midpoints. So 1.5 squared plus 1 would be this midpoint here. So doing that, take a second and do that, and you should get, 1.25 times 1 plus 3.25 times 1 plus 7.25 times 1. Ran out of room. Plus 13.25 times 1. So then my area here would be 25. Notice that's a lot closer than to the actual area that we found using definite integrals than either the left or the right hand. Okay, so let's look at an example where this is the only way we're going to be able to do this. So remember, I said that these work best, the Riemann sums work best for approximating values of definite integrals when we're given incomplete data, either an incomplete graph or an incomplete table. We really don't know what the function is. Maybe it's not a function that we could find really easily. Here would be a perfect example. A traffic light turns red and the driver stops the car in 5 seconds. Over those 5 seconds, the speed in feet per second are recorded. The graph below plots the points. Now, they also gave us a table of values that correspond with those points. And a question may say, let's find the integral from 0 to 5 of v of t dt using L5. So if we're using L5, it means we need to use 5 rectangles that start from the left. And we're trying to find the area under the curve. Well, I can't find the area under the curve using a definite integral because I don't actually know what this function is. So I'm going to have to use the left hand. So I'm going to connect left hand, and I'm going to first, before I do that, let's figure out what my delta x is, or delta t, I guess this variable is. Let's use t. Delta t is going to be, it's going to be the ending point of my interval and the beginning point of my interval subtracted, divided by how many rectangles we want, which is 5. So I know my delta t is 1. Well, I could probably guess that just by looking at this picture. And each of those rectangles is going to come at one of the second marks. So my left hand is going to start at the left and go down. So my left hand looks like this. Now in this case, notice my left hand is going to be quite a bit bigger than the actual value, just because each of my rectangles is quite a bit taller. So let's look at a succinct way we can write this. I know this area is the width of all of these is the same. So each one of my heights is going to be multiplied by the width, which is 1. And I have heights of, well, let's see. I don't know what this number is. Thankfully, they gave me a table and told me it's 88. And then my next height right here is 60. And then my next height is 40. Thankful for that table. Next height is 25. And then the last height of this rectangle, the fifth rectangle, is 10. Notice I'm not using that last rectangle. It's not part of the left grouping of rectangles, at least for 0 to 5. And so I would get that this area is 223, and that unit would be feet. The area under that curve would be feet. Okay, so let's do that again, but let's do it for the right Riemann sums, because this one says right 5. Well, the delta t doesn't change. So now let's draw my rectangles so they connect at the right. And you'll notice this last one doesn't actually look like it forms a true rectangle. Okay, where its right endpoint is here at 5. Notice we're connecting the right corner of the rectangle for the right-hand sum. Okay, now I want you to watch the table of values that we do and watch what we're using. The width of each of those rectangles is still 1, so I'm going to pull that out. And notice this time my first rectangle has a height of 60. And then my next one has a height of 40. And then my next one has a height of 25. And my next one has a height of 10. And my last one has a height of 0. Yes, I probably don't need to write 0, but I'm going to write it anyway. And so when I sum all of these together, and this is going to be an under approximation, I get 135 feet. Okay, you'll notice on the table of values, however, when I do this, if I'm finding the left-hand sum, notice I'm using the leftmost values. And if I'm finding the right sum, I'm using the rightmost values for the height. Keep that in mind. That'll come in handy when we look at just a table. Now it says interpret the meaning of this and give correct units. Well, if we're talking about a velocity graph and I want to interpret the meaning of this and I'm finding the area under the curve, which is the antiderivative of velocity, I'm finding the distance traveled from 0 to 5, or from when t equals 0 to t equals 5. Now, I already said it's in feet, but maybe you didn't understand that that was in feet. So let's look at a picture of it really quickly. If I have a rectangle from up above, so let's just pull one of the rectangles, I know this x dimension is in seconds, and this y dimension is in, feet. But I'm too close to the corner. It doesn't like it. Feet per second. You're just going to have to go with the fact that it says feet per second. And I know area equals base times height. Well, my base is seconds, and my height is feet per second. And when I multiply these, I am left with just feet. So if you ever get stuck and can't quite figure out what it should be, think about the rectangle and what the units are and how does it impact the whole problem. Okay, now I want to talk about so those are the Riemann sums. Hopefully you don't have any questions so far, but we're going to look at one other type of approximation that's not actually called a Riemann sum, but it's always lumped in together. The next thing that we're going to talk about is what we call the trapezoid rule, or the trapezoidal rule. And it is just another approximation technique that's used, and I think you're going to see it's probably going to be even more accurate, but it's not truly a Riemann sum because it's not a rectangle. Now, picture a trapezoid where the flat part, A flat part, not the base or the height, is attached to the x-axis. And maybe instead of drawing a rectangle, we draw a trapezoid that looks something like this. Okay? Well, we know in a trapezoid, the area of a trapezoid, as long as that is perpendicular, we may call this base 1 and this base 2. Then this would be the height. The height is what connects base 1 and base 2. And the formula for area is the height divided by 2 times base 1 plus base 2. Think all the way back to geometry for that one. Now, if we're looking at a graph, if we're looking at this in relationship to a graph, then this height is actually that delta x. It's that tiny little width that we're using. And then b1 would be f of our first x term. And b2 would be f of our next x term, keeping in mind that those could keep shifting up as we keep moving our trapezoids up the x-axis. So then the area that we actually are going to use is going to be delta x, that width divided by 2, times f of x1 plus f of x2. Now let's look at what that looks like. Okay, so let's approximate the area between the function x squared plus 1, which we've already looked at, and the interval 0 to 3, so rather than 0 to 4, using 3 trapezoids. Okay, so when it says we're using 3 trapezoids, I still need to go through and figure out what my delta x is. Now it's pretty obvious if we're going from 0 to 3 and I'm using 3 trapezoids that my delta x is just going to be 1. But mathematically we take the end of the interval, that b value, minus the beginning of the interval, the a value, and divide by the number of rectangles, in this case trapezoids, so divide by 3. So we get delta x is 1. Well, that makes sense that each of my trapezoids then is going to take up 1 unit along the x-axis. And when we draw trapezoids, we're going to connect the 2 endpoints and draw in a trapezoid. And what you'll see is sometimes these are hard to draw because they hover so close to the curve, or we don't draw straight like that last one I just drew. And then this one's going to be even tighter. Okay, so you can see our trapezoids there. Now, when I go to find the trapezoid, the area of the trapezoid, I would do 1/2, delta x is 1, divided by 2, times my first point. Well, this was the ordered pair 0, 1, so my first height is 1, and my second height is 2. And then I would do that again for the next trapezoid, where my left-hand height is 2, and my right-hand height is 5. And then I would do half of the left-hand height, which is 5, plus the right-hand height in this case, which is 10. Oops, that's supposed to be a 3/10. And then when I sum these together, you may see them written like this. You may pull out that 1/2. You may even notice that there's going to be 2 of each of the center ones, not the endpoints. So you may see those grouped together as well. Really, I don't need to do that. This has pretty simple math, so I'm just going to do half of 25, which means my area is going to be 12.5 using the trapezoidal rule. So let's just check that. Let's just see what the definite integral tells us it should be. So if we go from 0 to 3 of x squared, oops, that was supposed to be just an x squared, no negative, of x squared plus 1 dx, we'd get x cubed over 3 plus x evaluated from 0 to 3. So we'd get 3 cubed, which is 27 over 3 plus 3 minus 0 over 0. So we get 9 plus 3, and we get 12. So the actual area is 12. This gave me 12.5, and I'd say that's a pretty good estimate. I mean, we can see where the overage is. We can see these little places where it's just a tiny bit over what the actual area under the curve is. Okay, let's move on and look at a table example. Okay, here's a perfect example why we would need to use Riemann sums. Table below shows select values, meaning not all of them, of the velocity of a small camera drone as it traveled down a golf course for 60 seconds. I don't have a way to write a definite integral here, so we're going to have to use something other than those integration techniques that we've known so far. That's where our approximation comes in. This says estimate the distance traveled. So if we've got the velocity and we want to estimate the distance traveled, we know we need to find the area under the curve. So we're going to have to use that approximation. So estimate the distance traveled by the drone using our approximation methods. So we're going to look at this 4 different ways just to see how close it all is. Let's start with our left-hand sums. Now, I forgot to write in here, but let's let delta t be 10. Okay, so delta t is 10. So if I look at my left-hand sums, if you picture this on a graph, the width of each rectangle is going to be 10. That's what it says, delta t is 10. Now, normally you'd either have to calculate it or it'd have to be given to you, and I didn't do either, so I'm telling you now. So my left-hand sum, or my width of my rectangle, will be 10. Using the left-hand sums, remember from that example on that graph with the traffic light, I'm going to start with the left-hand corner is going to be at 0, the first rectangle. And the next rectangle, it's going to be at 28. And the next rectangle, it's going to be at 31. And the next rectangle, it's going to be at 33. And the next rectangle is going to be at 23. And then the last rectangle is going to be at 27. Why is it not at 15? Well, if we think back to that last graph, whatever happens with this graph, all of my left corners to make 6 rectangles, I'm sorry, this case would be 1, 2, 3, 4, 5, 6 rectangles. I can't use that last term because I've already taken up that width. So this would be the left-hand sum. See, we're using all the left-hand values of the table. And if I sum this up, I'm going to get 1,420 feet. So hit pause and see if you can find, see if you can find the right hand and the midpoint, maybe even the trapezoid, and then come back and check. Okay, hopefully you had a chance to try the right-hand sum. Now that width is still 10. And so when I look at the width here, if I look at the right-hand triangles, or rectangles rather, I'm going to start at 28, then add 31, then add 33, then add 23, then add 27, and then add 15. Notice now I'm using all of the right values of my table of values, and you should get 1,570 feet. Okay, now I shouldn't have let you try the midpoint one because the way this table is written, I couldn't use delta t equals 10 because I'd have to guess at the value, and I can't do that. So let's, on this midpoint one, let's let delta t be 20 instead. So if you'd like to hit pause and try it with delta t being 20, great. If not, follow along. So if I know the width of my rectangle is 20, that means this comprises one rectangle. And so the midpoint of that is going to be this 28. And the midpoint of the next rectangle would be 33. And the midpoint of the next rectangle would be 27. So to do my midpoint sum, I don't know why it keeps rotating tonight. The midpoint sum, I would do 20 times 28 plus 33 plus 27, and we'd get 1760. And then finally for the trapezoid. Trapezoid, we're going to stick with delta t is 10. So on this trapezoid, we're still going to use delta t equals 10. Let's do the trapezoid in a different color. Okay, so we know a trapezoid, the height is going to be the number of divisions divided by 2. And then my first trapezoid is going to have a base of 0 and 28. My next trapezoid are going to have bases of 28 and 31. My next trapezoid is going to have a base of 31 and 33. My next trapezoid is going to have 33 and 23, then 23 and 27, then 27 and 15. So this would be all of my trapezoids. This would be trapezoid 1, trapezoid 2, trapezoid 3, 4, 5, 6, where each of them are multiplied by the base and the height. And so if I do those calculations, I get 1495 feet. How are we doing so far? Okay, well, there is a way to determine whether our approximation will be an overestimate or an underestimate. And it all kind of depends on what we're given or what we're looking for. So this says give a hypothesis for when you will get an under or overestimate, depending on which type of sum you use and the function's behavior. So I want you to take a second and think about what it means to be concave up and increasing, what it means to be concave up and decreasing, concave down increasing, concave down decreasing. Maybe draw for yourself a picture. Okay, hopefully I'm going to come over here. I'm going to make another table. So these are going to be my increasing and my decreasing. And concave up. If I have an increasing concave up graph, do you agree it might look something like that? And a decreasing concave up graph might look like this. And an increasing but concave down graph would look something like that. And a decreasing concave down graph might look like this. So if I have left-hand sums for this increasing concave up, is it going to be an over or underestimate? Hopefully you said under. And it's true. It's going to be an underestimate because the left is under the area. So what about a right-hand sum in this case? Well, that should make sense that it would be an overestimate because the right is greater than the area. Okay, hit pause and try all the rest of them. Okay, coming back to this, if we go left hand, decreasing, this should be an overestimate because the left would be greater than the area. And the right would be an underestimate because the right is less than the area. And we can see that right here. Where's the right hand? We feel good with that one? Okay, so left hand concave down. Hopefully you got underestimate. Right hand should be over. Left hand decreasing should be over. And then under. Okay, so if you were to make a general statement about the left rectangle approximation method and the right rectangular approximation method and how it relates to these graphs, what would you say? Hopefully, you would say that the left and right approximation depends on whether the function is increasing or decreasing. It doesn't really matter its concavity. If the function's increasing, the left hand is always under and the right is always over, an overestimate. Okay, well, let's look at that as it relates to the trapezoid. See what you think. So take a second, maybe draw trapezoids on each of these four and see if you can come up with a general statement about the trapezoid, what it depends on. Okay, so drawing in my trapezoids. If I were to draw in my trapezoid here, I can see that this would be an overestimate. Whereas my trapezoids here will be an underestimate. This one will also be over. This one will also be under. So if you were to make a general statement about trapezoids, what would you say? Does it depend on the increasing, decreasing, or does it depend on the concavity? Hopefully you said the trapezoidal rule depends on concavity. Doesn't matter if it's increasing or decreasing. The increasing could be either over or under. It's whether it's concave up or concave down. Okay, just something to think about as you go through here. All right, ready to try one full example? Here we go. Okay, so the table below represents the velocity in feet per second of a car traveling on a straight road over 50-second time interval. We want to estimate the distance the car traveled over this interval, using the table along with a graph for your computations. So the first thing it says is estimate the total distance traveled by using a left Riemann sum with 5 partitions of equal length. Draw the rectangles on the graph in colors. So we'll do the left, since we've done all the lefts in blue. We'll do them in blue. Okay, so first thing we want to do is figure out what our delta x needs to be. Well, we know the highest point is 50, the lowest point is 0 on the t-axis. I probably could have done delta t. Anyway, we want 5 rectangles. So each delta x is going to be 10. Okay, hit pause, graph your rectangles, see if you can find the left-hand area. All right, hopefully you had a chance to try this, and if you draw in your left rectangles, they look something like this. So there's my left rectangles. Okay, and the area here is the width of each of the rectangles is 10, and the height of the first rectangle, thankfully we've got it, is 0. The height of the next one, 20. The height of the next one, 52. Height of the next one, 80. Height of the last one looks like 77. And that sum is 2290. And that unit would be feet because we're doing velocity in feet per second. And this is just seconds. So feet per second times seconds would give me just feet. All right. If you didn't get a chance, hit pause, see if you can do the same thing for the right Riemann sums. All right, hopefully you had a chance to draw these in. I'm going to draw these in green. And there we go. So you can see those in there in green. They're kind of funky in there. Hopefully you can see the difference between those two. The width of the rectangle is still 10. But this time the height of my first rectangle is 20, then 52, then 80, then 77, then 74. And so then this total area is 3,030 feet. How'd you do? All right, we're going to repeat this process. So I gave you a separate graph for it just because otherwise it gets really convoluted. So in part C and D, see if you can hit pause and try this problem. Okay, so I brought down the table just so you could see it. So let's do the midpoint, and let's do that. Oh, I don't know. We'll do it in red. So the midpoint with 5 partitions. Well, one was already drawn for us. So you can see that the midpoint dots are already in the graph, so that helps. And so your midpoints should look like this. Oops. And if I go to find the area of this one, we'd get 10 times 14, because it's the midpoint of this rectangle. Midpoint of this rectangle is 28. Midpoint of this rectangle is 70. The next one's 86. And then finally 70. And so if I sum all of those up together, I'm going to get that the area is 2680 feet. Okay, so now let's look at the trapezoid sum. And if we look at the trapezoid sum, if I draw my trapezoids in here, oh, that one didn't go straight. None of these are super straight. Sorry about that. So if I do my trapezoids, I know that this is going to be 10 divided by 2. My first trapezoid has a height of 0 for one side and then 20 for the other. My next trapezoid then has a base of 20 and 52. And then my next trapezoid has a height of a base of 52 and then 80. And then I have one of 80 and 77. And then I have one that's 77 and 74. So this area is 2660 feet. How'd you do? Okay. One fun trick that we can use. First, I would like you to take the answer from part A and part B, and I would like you to find the average of them, please. So for L5, we got 2290. And for R5, we got 3030. And if I go and find the average of those, let's do that. If I do 2290 plus 3030 divided by 2, we get 2660. How does it compare to the trapezoid sum? It's the same. It's the exact same as the trapezoid sum. So here is a hint for you. If you want to do the trapezoidal rule, and you've already done the left and the right, you can take the left hand and the right hand and find their average. Hopefully you see the benefit of the Riemann sums and why we would actually use them. Obviously, our integration techniques are the best way we can go, but not always do we have complete data. So this is a way that we can find area under curves. All right, you guys, have a great day.